Okay, so welcome everyone. Yeah, hope you had a good break. We we haven't. So last week was recess week, and then for the previous 2 weeks we didn't meet because I was traveling. So you were supposed to be working on the tasks for FM and PCM, right? So let me just remind you. Let's go to Piazza. Give me a second, and I will log in and let me share my screen. Okay, it's a bit slow because I think I'm on my phone. Okay, yeah, it is a little bit slow. Okay, let me share my screen. Okay, so you guys can see my screen, right? So maybe if you don't mind, I'm gonna just ask you every now and then if you can hear me and if you can see my screen. And I appreciate it if you guys could just quickly answer me. So can you guys see my screen?
Yep, can hear you too.
Okay, good. So you were supposed to be working on, if you remember, yeah. So we had a task for frequency modulation and the task for PCM, right? So, and your PCM homework is due this on this coming Monday, right? March 3rd is next week, yeah. Okay. And then you also were supposed to collect your SDR. Can I just check, has everyone here already collected their software radio? Can you give me a show of hands if you have collected it? Just maybe raise your hand. Yeah, so most of you looks like most of you have collected it. What about the rest of you? Yeah, maybe there's a bit of delay. Changfei, you haven't? You put up a
I put out already.
oh, okay. No, it's just that the the reaction you put up is like some arrow, right? Ah, okay, there we go. How about Tiru Kumaran and Yang Bowen and Tin Yu? Have you guys picked up your software radio kit? Okay. Yeah. So are you able to give me a like the reaction, the Zoom reaction? Like raise your hand. And Bowen, yeah. Can you guys just try? I mean, yes, it's great that you're writing to the chat, but it'll be easier in future if you can raise your hand. Yeah, okay, good. And Bowen, are you able to raise your hand in the Zoom chat? In the Zoom reactions? Do you know how to do it? Yeah, Yang Bowen, you can respond to me. Okay, great, perfect. Okay, so everyone can do it. So you were supposed to have done lab 0. So can I check with you if if everyone has completed lab 0? So this time I'm going to flip the question around. Let me clear the feedback. And if you're having any problems with lab 0, can you raise your hand? Because if you're having problems, what we'll do is I or the TA will help you. So for folks here, if you're having a problem with lab 0, please raise your hand. If you don't raise your hand, I'm going to assume that at least all of you, the 12 people here, you are okay. There's 8 people here who are not here, but at least the looks like the 12 folks here have been able to do lab 0, which means you've set up the software that's necessary to do the lab. So you can now start to work on lab 1. Okay, I think lab 0 is due today, right? Am I correct?
Yes.
Yeah, so that means by today, everyone should submit lab 0. Right, lab 0 is due, yes, on this Tuesday. And then your PCM homework is due on Friday. So what you can do is you can ask me questions, okay? If you have any questions. right? The PCM homework is due this Friday, correct? PCM. Wait, when did I make it due? Hang on. I made it due on Tuesday. Wait, hang on. Just trying to see our schedule. Yeah, it's due this Friday, correct? This Friday would be March 3rd. Yeah. So today is a good day for you to ask me questions about the PCM homework. And then lab 1, actually I should share with you what I'm looking at. This is our schedule. Right? This is our schedule that I distributed to you guys. Right? Can you guys see the schedule?
Yes.
Yeah. So we're gonna kind of live by this schedule, okay? So right now we are on February 28th, right? And actually, there's gonna be a slight change. On this, I indicated we should be starting digital modulation, but actually, I haven't uploaded the material for digital modulation yet. And actually, I think we have a quiz coming up, so it's better that today we review AM, FM, and PCM. So in preparation for the quiz, okay? So that's what we're gonna do. All right, we're going to. So I'm gonna shift these down. I'll send you an updated schedule, but roughly, we'll do the digital modulation not this week, but rather next week, right? So and by the end of today, after class today, I'll upload the material for digital modulation, and then you can work on it over the next week, and we can start talking about it over the next couple of weeks. So things will shift down by 1 or 2 weeks, but that's okay because we have a little bit of slack at the end here. Okay, so but you just I'll send you an updated schedule, but the due dates don't change. Okay, all the due dates right now are going to remain the same. Okay, I may push some of the homework due dates, but the lab due dates are not going to change. Okay, so this is what you should be doing. But yeah, I was just concerned because I haven't seen you for a couple of weeks, so I wanted to make sure that all your questions about FM and PCM are answered. All right, so that's what we're gonna do today. We're also going to, as I mentioned, if you go to Canvas and you go to Files, and you go to Activities, I put up sample problems here. Okay, and we're going to use these sample problems as a basis for the discussion today. These sample problems are problems from Fourier transform, amplitude modulation, frequency modulation, and PCM. So they're a good summary of what we've been doing. They're a good summary of what you should know and should be able to do, and they're good preparation for the quiz. So you can almost think of these problems as sample quiz questions, right? Okay, good. So any questions before we move on? I'm going to start with FM. We'll move on to PCM, and you guys can share your questions if you have any. Yeah, is that sound good?
Yes. Okay.
Yeah, okay. So let us do this. Let me close that. I'm going to open up the handout for FM. I think I mean the for FM and PCM, I shared with you, right? If we go here, you go to videos. I've shared with you the Zoom lectures, right? From last year, from last semester, right? So these are the bite-sized videos. Where did I put the Zoom? Oh, did I just make it? I can't remember. How did I share it with you? I think I gave you the links, right? It should be in Piazza, right? Yeah, I think I remember doing that. Let me see. Oh yeah, right. So these were the past year Zoom recordings for FM and PCM. So I hope you guys watch through this because this was a kind of the replacement for the live session. But you know, I didn't want to shortchange you. So in this live session here, I want to open up the opportunity for you to ask questions. Yeah, was there did somebody say something?
No, sorry, Prof. I forget to off my mic.
No worries. Who's that? Is that Kenley?
Yes.
Yeah. No worries. No worries. Yeah. Just if anybody has any questions, please just ask. Okay. So these past year Zoom recordings shown on Piazza here, right? They should have been helpful for you. Now, so FM. Let me open up my FM notes. Right. So there was. Let me see. Actually, I wonder if I can open this in my browser. Then it'd be easier because I already have the browser here, right? Let me see. Nice, good. So you guys can see it, right? If I open it up here. So this was the intro, the analysis, and the example. Okay. And for all of these, there were videos, right? And especially for the example, I went and I made a video for you guys, right? Okay. So maybe I just give you the opportunity to open up the floor for questions. Do we understand everything about FM? Right? I mean, the key idea, one of the key ideas in FM is that, well, you're going to, if you look here, what we are going to do so FM and PM fall under angle modulation. What we're going to do is we're going to look at the argument of the cosine. So this is my carrier, and the argument of the cosine is going to carry the information signal, right? And when this argument here depends on the instantaneous frequency, we call it frequency modulation. When when the phase depends on the message signal, we call it phase modulation, right? So that's the idea here. And both for phase and frequency modulation, we have a deviation constant. This deviation constant determines how much effect the message signal has on the phase or the frequency respectively. And then again, I'm not going to turn this into a lecture. I think you guys already know the lecture. I mean, you've already been through it. But what I will point out is that we use something called this rule of thumb called Carson's rule that allows us to estimate the bandwidth of an FM or PM signal. And Carson's rule is given here. Is basically right here. So down here is 2 times beta plus 1 times W. W is the message bandwidth, and beta is the modulation index. And the modulation index is defined here for phase modulation and frequency modulation here in equation 3. So this equation right here, equation 3, shows you Carson's rule. And so this is one of the takeaways from this. Then we in the video you talked about generating FM and about demodulation of FM. So can I check if we have any questions? Right, and then remember in the video we talked about the phase lock loop. The phase lock loop is sort of the phase lock loop tracks the frequency. The phase lock loop was also something we saw in AM when we wanted to do synchronization, right? But the phase lock loop basically tracks the frequency and phase so that things remain in sync. But you notice that in FM, we're actually changing the frequency and phase. So if you can track it, you're actually getting the information. That's why the phase lock loop works as a demodulator of FM and PM. Okay, and I think that's it. And then there was some example here. Okay, so can I check? I'm getting a sense there are no questions, but I give you maybe 10 more seconds. If you have questions, please raise your hand and ask it. So 10, 9, 8, 7, 6, 5, 4, 3, 2. Last chance, 1. Okay, actually not really last chance. If you have questions later, please feel free to ask. Okay, so that was frequency modulation, right? Maybe somebody can tell me, maybe Jie Kang, are you here? Yeah, Jie Kang. Can you tell me what's the main difference between AM and FM?
So can you repeat the question?
Yeah, what's the main difference between AM and FM?
You see, you modulate different things. You modulate one is you modulate analog, one is modulate frequency,
So what's AM?
amplitude.
No, so you said you modulate different things. What does that mean? Can you be a little bit more precise? Or just elaborate a bit more? What's the main difference between AM and FM? Is it
Sorry, okay. One moment. Let me.
okay? Don't worry. Okay, does someone else want to help? Ken Lee, you want to try? What's the main difference between AM and FM?
AM is to use the amplitude to do modulation,
Yeah,
and FM to use the frequency without changing the amplitude to do modulation.
yeah, that's right. So you can say, what is this? I want to hang on. Let me try a different color. Can I change the font size? Don't quite know how to change the font size. Okay, anyway. Can you guys see this? Can you read this?
Yes. And,
It feels too small, but okay. Maybe we'll stick with it. So the main difference between AM and FM. Yeah, so both of you are right. Actually, Chiekang, you weren't wrong. I just wanted you to explain a bit more. Is okay. In AM, we encode the information or message in the amplitude of the carrier. And so Jiekang, can you fill in the blank for FM?
We encode the information or message in the frequency of the carrier.
Yeah, exactly. And of course, like for example, if we were talking about phase modulation, then we would say in the phase of the carrier, right? Okay, so we've now finished studying AM, FM, and PM, right? Okay. So everybody good, sorry, everybody good with that? So shall we move on to PCM? That was not a rhetorical question. I want to know if you guys are good with FM, and we can move on to the next topic that you were supposed to do, which was PCM. Okay, so Ken Lee, thank you. But for the rest of you, try to keep up. I mean, like it's a little bit boring for me if I have to talk to myself. So it'd be nice if you remember our agreement for turning this into a remote session was that we would still interact, right? So I ask you again. So is FM good? Can we move on to PCM?
Yep.
Good. Thanks. So a few of you are answering. I would like the rest of you to pipe in. This is not meant to be a passive exercise, right? As I said, if we're not going to get interaction, we'll go back to face with no Zoom. Okay, so it's kind of up to you guys. Okay. Okay, so let me bring up the notes for PCM. Where were they? Here we go. Okay, so PCM stands for pulse code modulation, and PCM is the bridge, right, from analog to digital, right? So when we talk about the bridge from analog to digital, we do sampling and quantization. Sampling is discretization in time. You take time and you go from continuous to discrete, and then quantization takes value and makes it go from continuous to discrete. Now, sampling we've already studied because, well, not in this class, but you studied in your signals class, right? sampling is all about Nyquist rate. So can somebody remind me, what is the Nyquist sampling theorem or result? What does Nyquist tell you? I'll give you a second to think about it. I'm asking you, what does Nyquist theorem tell you? It tells you something about sampling rate. What does it tell you?
Sampling rate needs to be 2 times of the bandwidth in order to fully replicate the signal.
Yeah, that's right, Chiekang. But it's a little bit slightly different. You're almost right. Nyquist sampling theorem tells you the sampling rate needs to be at least twice the bandwidth, right? Meaning it can be larger, right, Jiakang? Can you
Yep,
sample
yeah,
a
can be
fraction
larger.
of them?
Can be larger, but at least
Yeah,
2
so
times the
at
bandwidth.
least, yeah. So pretty much that's all we need to understand about sampling, right? With that in mind, we kind of understand everything about sampling. Okay, so hey guys, just give me a okay, sorry, I'm back. Yeah, so so sampling is done. Then in this set of notes, we primarily focus on quantization. Okay, and quantization is the task of discretizing the value. And this was an example of a midpoint quantizer. So can somebody explain this to me? How does this quantizer work? Who's going to be brave and explain it to me? How about, can I call on someone? Tintin, do you understand the quantizer?
Sorry, Prof. I haven't got time to watch the lecture yet.
Okay, that's fine. but I appreciate you like responding to me and telling me. So that's good. But so can I ask you to please go through it? Because so this applies to all of you. If you get behind, it's going to be hard to catch up. Okay, so someone else, how about you, Lian? Did you get a chance to do the quantization, the PCM?
No,
Sorry, yeah, please go on.
sorry. Okay.
Sorry, did you say yes or no?
No, yeah, no watch yet.
Okay. How about I just ask for someone who has done it? Can you explain this?
Oh,
this?
I can try.
Yeah, Kenley, please go ahead.
I think it's about breaking into bins. So every bin has its representative value. With choosing time as one of the sampling points. So matching to the value of the bit. Yeah, I think that's what I understand.
Yeah, that's not bad. I wonder, let me see. Let's see if we can get a animation of quantization online. Let's see if we can find a good idea of quantization. Well, so for example, all of you already know about quantization when you like for images, right? So for example, we quantize the number of bits per pixel, right? So let me give you, let's see if we can hang on, give me a second. I'll find a picture of myself so no one can say, oh, how about a picture of a butterfly? Let's see if we can get a picture of it. Okay, so this is cool. Let's do this one. I like this picture. Can I copy the address? Let's go here. Oh, I have to do this from my, that's not what I want. Okay, hang on. All right, let me save this then. We save image. Okay. I go here, downloads, butterfly. Okay, so now here's the butterfly. Let us I haven't tried this, but let's say we did it to 3 colors or like 4 colors, right? You can see that when you limit so if you limit it to 4 colors, then there's only like two bits per pixel, right? So you can see that when you do that, it doesn't look as good, right? So that's the same, because what we're doing is we're binning the color, right? If I went to just like 1, you get nothing. If I went to 2, you get a black and white image, because it's either 1 or 0, right? So it's the same idea when we are building this quantizer. I wonder if we can get a better, I wanted to show you, let's see, let me see, midpoint quantizer. Yeah, maybe it's going to be hard to find one. Yeah. I thought there should be. Ah, okay, this is good. The pictures are good. So, for example, so let's take a look at this picture here. Or let me find one slightly higher resolution picture. Maybe this is good. This is good enough. Can you guys see this?
Yes,
Is it?
can see.
Yeah. So this is a signal here, and right, this signal takes all values, and we've sampled it at these points here. So, for example, right, we're sampling it at these points here, here, right? These are my sampling instances, my sampling times. Now, these right here, these are my quantization levels. So what happens is anything that's near this gets mapped to this. So for example, take a look at this point here. Right, this point is here, but when we store the sample at this point, we're going to store this value. That's quantization, right? So you can see that, for example, this point is stored like this, and this point here is actually stored like that. So what we are doing is the red curve is an infinite number of points, right? Infinite number of values. But the quantize here only take on 1, 2, 3, 4, 5, 6, 7, 8 values. So, and these 8 values, they are the quantized values. So for example, if I can go back here, maybe we can, let me close this. Wonder if I can see both. Here we go. This is a good picture here. Because what this picture shows you is both the original signal and the quantized signal. So the blue is the quantized signal. The red is the original signal. So does everybody understand quantization? At least the process from this picture? So for example, Tintin and Lian, you haven't gone through it, but from this picture, can you understand quantization?
Yes, bro.
Yeah, so, right, so the idea is that we store only one of these 8 values. We don't store the values on the red curve. Okay, what about you, Lian? Is this clear?
Yes, Prof.
Yeah, okay. So so I'm spending time on this because I don't want you to get stuck in the math. You need to understand what quantization is first. Then we can talk about analyzing it with the math and equations and all that good stuff. Right? There's no point in trying to do the math if you don't understand the basic function, right? So this is quantization. And this is a 3-bit quantizer. With 3 bits, so maybe Kenley, with 3 bits, how many levels can we have?
You can have 8 level or
8 levels. And how do you get 8?
to a power of 3.
Yeah, 2 to the power 3. So you can see that with 3 bits, we have 8 levels. The blue curve is like an approximation to the red curve. So let's say we were to, for example, so I like this picture a lot. I wonder if I can, with this same picture, I'm gonna try something. So how about 3-bit quantization? So that shows you this picture. I want to show you 4-bit quantization. I want to compare 3 and 4-bit. Here we go. So you can see this picture here and compare to this picture here, right? So we have this one. This one is how many bits is this, Kenley?
This 4 bit
Yeah, and then with 4 bits, how many levels do we have?
to the power of 4.
Which is
16.
16 levels. So you can see there's 16 levels. And can you see that this blue curve is a much better approximation to the red curve as compared to this, right? Can everybody see that? That when you compare the 3 and this is this one. When you compare the 4-bit and 3-bit quantizer, right? You can see that the blue curve here is a much better approximation than the blue curve here. Because when you add more bits, you can have more levels. Now, Jiakang, you asked a question on Piazza about bitrate, right?
Yes.
So which one of these quantization methods will have a higher bit rate? Given the same signal, which one will have a higher bit rate? The 3-bit
4-bit
one or the 4-bit one? Yeah, because each sample is represented by 4 bits, right?
Yep.
Here, each sample is represented by 3 bits. So this has
Lower
what?
bit rate.
Yeah, I mean, this has a lower bit rate. This one has, you're going
A
from
higher one.
3 to 4, so it has about 33% more, right?
Yep.
Yeah, so now how would you compute the bit rate at the output of the quantizer? Well, you would look at how many, so you would say something like, samples per second, right? Multiplied by what, Jiakang? Bits per sample, right? What is samples per second times bits per sample?
Bits per second.
Yeah. It is, right? The units
Yeah.
differ, don't they?
Trying to
this
cross
is,
multiply in my brain.
yeah, so yeah, no, well, the samples cancel and you're left with bits per second, right?
Yep.
So that's exactly right. So this is how you compute the data rate, the bit rate that the quantizer gives you. You have to look at the sampling rate and you have to look at the bits per sample. So what does the sampling rate depend upon? So Tintin, what does a sampling rate depend upon? So if I give you a signal, how would you determine what your sampling rate should be?
No idea, bro.
That's okay. Somebody want to help, Tintin? How about you, Shujin or Shuijin? Li Shuijin? How does the
Yes.
Hi.
Based on the bandwidth of message signal.
Yeah, exactly. So Tintin, you get that? If
Yeah.
so, do you remember the Nyquist sampling theorem? Says that your sampling rate needs to be at least twice the bandwidth.
Oh.
So if I give you a message signal and I tell you the message, for example, message bandwidth is 2 kilohertz, then Tintin, what's the minimum sampling rate?
4 kilohertz.
Yeah, so that's 4 samples per second. And then if I tell you I'm using a 3-bit quantizer, what's the bit rate at the output of the quantizer? A 3-bit quantizer for a 2 kilohertz signal. What's the minimum bit rate at the output of the quantizer? Are you with me, Tintin?
Yes, Prof. I'm thinking. Sorry.
No, I want to make sure that I want to make sure my internet is not out again. You know, I'm still tethering from my phone, so it's okay. Take it. Take your time. Take a moment and think about it. And again, if you don't know, it's fine. Okay.
Okay.
Does somebody want to help, Tintin? How about you, Changfei? Changfei. So the question is, I have a 3-bit quantizer for a 2. What do we say? Tintin, what's the message bandwidth I gave you?
2 kilohertz.
Okay, for 2 kilohertz signal. 2 kilohertz bandwidth signal. What is the bit rate at the output of the quantizer? That's the question being asked. And just so Tintin, that the answer is right here. Right? This right here is the sampling rate. This is the bits per sample. So you can think of it almost like this, okay? You have a box here, okay? So an analog signal comes in here, okay? And this is my sampler sampling at fs, okay? And this is going to output a bunch of samples, right? So Tintin, for example, if I have a 2 kilohertz signal, what's the minimum sampling rate?
4 kilohertz.
Yeah, so that means there's 4,000 kilo, 4,000 samples per second, right?
Yes.
Right, it's 4,000 samples every second. Okay, now each of those samples uses how many bits?
Well,
I've told
3
you right.
bits. 3
Yeah.
bits.
So can you tell me? So let's say this now is going to go to another box here. That's going to now generate bits. And this is going to be 3 bits per sample. Okay, 3 bits per sample. So can you figure out how many bits are coming out here per second?
12,000.
Yeah. See, when I draw a picture, you know how to do it.
Yeah.
Right, so this is going to be 12 kilobits per second. Right, so now we see, oh, okay, the sampling rate and also the quantizer parameter determine how much information I have to transmit, right? Or for example, maybe this is for storage, how much data I have to store. So is this clear, Tintin, now?
Yes, bro. Thank you.
Okay, good. Okay, so all these things are actually here, right? They're right here. This right here, this slide is essentially that right here. This 2WN is right. This is a n-bit quantizer, bandwidth W, you have to sample at least 2W. So this is essentially, yeah, I call it the pulse transmission rate, but Jiekang, do you see that this is also, since each bit is represented by a pulse, is also the bits per second.
Yes.
Okay, so everybody good? So that's a little bit about the effect of the quantizer on the rate. But now the question is, how do I determine n bits per sample? We know how to determine the sampling rate. Depends on the bandwidth. But how do you determine the bits per sample? That is quantization. Okay, and what we're going to do, just like you saw, the more bits per sample you have, then the less error you have. Can everybody see that? When I look at this, you see that you can almost look at this space. So the space between the blue and the red is your error, right? That can everybody see that? The space between the blue and the red is your error. And you can see if you come here, these spaces are smaller, right? Because I'm using more bits per sample. So we can see that the more bits per sample you use, the better you can represent and the less distortion you have from your original signal, right? But we see, Tintin, what's the difference between the 3-bit and the 4-bit quantizer? What's the difference in terms of how much data it generates? Which one generates more data?
4 bits.
Right. So that's the price you pay. If you want to get a better signal, you have to pay the price of sending more data or storing more data. Okay. And what the rest of these notes do is they try to set that up. Now, I'm not going to turn this into a lecture on quantization. You just watch the video, because in the video, it tries to be very clear. It goes through these notes and it explains it very, very clearly. Jiekang, you've been through the notes, right? And the video?
Yeah.
Yeah. Does it, am I correct? It explains these notes, right?
Yes.
Yeah.
I believe so.
Was there anything that was unclear to you, or are things okay?
Hang on. I think there was a question that I wasn't really sure about. Give me a moment.
Sure. Yeah, of course. What about you, Kenley? Have you been through the video?
Yes.
And does it explain the notes?
Yeah.
Okay,
I think looking at the note itself can't really know what's going on.
Right. That's
yes.
why I gave you the video, right? Because normally we would do this live, right? But we're trying this flip classroom experiment, right? But were you able to understand?
Yes.
Okay, great. So Jiekang, you had a question?
Hang on.
Yeah, sure.
I think the first question, because there's the signal, I find that there's 2 parts, so I wasn't sure which portion of the signal to use as to calculate the bandwidth.
Can you be a bit clearer? Is it in the notes or is it in the homework?
It's in the homework.
Okay. You want me to pull up the homework? Because this is
Also
also
can.
a chance for you guys to ask questions about the homework, you know? Let me find problem set 3. Hang on.
Because after I expanded it out, and then I realized that there's actually 2 parts.
Yeah, which
Signal
question?
2 parts. The first question.
Okay, given the signal, find the minimum sampling rate required for perfectly reconstructing the signal. So
I went with the higher one in the
yeah,
end.
of course you have to, right?
Yeah.
Yeah. So this cost times cost is like 1/2 cost of the sum and 1/2 cost of the difference, right?
Yeah. So there's
Yeah.
2 parts. One is higher, one is lower.
Yeah, it makes sense, right? I mean, if so remember that Fourier transform is linear, right? Because the integral is linear, right?
Yeah.
So if you have a signal, if a signal is a sum of 2 things, that one and that one, right? Then this entire signal is governed by this maximum, right?
Ah, yes.
So you're right.
Okay.
You are correct.
Okay, got it. Thank you.
Yeah, no worries. Okay, so that was that. I'll leave it up here in case somebody else has questions about PCM. So by the way, for those of you you haven't done it, you have a homework due this Friday. It's this PCM, and it's only questions 1, 2, 3, and 4. Okay, and I'm willing to give you some hints. Like this question 1 is quite easy because you just have to understand this. It's a cosine times cosine. It's a trigonometric identity. Okay, and that trig identity is this right here. Cos of A times cos of B is just cos of the sum plus cos of the difference. Right, so you just have to use this trig identity here. And so if you bring it back here, you're going to take the sum, which is 8,000 plus 8,200, right? Which is 16,200. But you got to write it as 2 pi ft, 2 pi f. So 16,200, 2 pi, so it's 8,100, right? The maximum frequency is 8,100. So what's the sampling rate? Is that what you got, Chekang? 8,100.
Yes. Yeah.
And then what's the sampling rate?
Sampling frequency 16.2.
Yeah, it's 1/2 of, sorry, it's 2 times 8,100. So there, I hope you were paying attention. I did problem 1 for you. Okay. This one, question 2. Chekang, this, I mean, I think this is a question you were talking about in Piazza. This is pretty straightforward, right?
Yep.
Just need to do exactly, Tintin, exactly what we did before. It is compute the data rate at the output of the quantizer. But here, instead of computing the data rate, I'm telling you that you have a maximum allowable data rate. So you need to pick the sampling rate and the number of levels, right? And the number of bits per sample, right? So that for the 3.2 kilohertz signal, you don't exceed that. So Tintin, for example, do you see how what we did before completely solves question 2?
Yes, bro.
Yeah, is that clear?
Yeah.
Okay. Then question 3, what is the resulting signal to noise quantization ratio for a signal uniformly distributed on -1, 1 when uniform? Yeah, this one is actually, you can't logic this out. This is based on our notes here. Okay, so on this page here, page 5, we are analyzing uniform distribution with a uniform quantizer. Exactly what this question is asking. Okay, and here there's no numbers, but here you have to plug in some numbers. So here I have 256 levels. All right, if you look here, this Q is what is this? This Q is just, I think this Q here, if you look at my notation, Q is the number of levels. Okay, so Q is here, and then there's a dynamic range from -1 to 1. In my example, the dynamic range is from A to B. So you just got to put in -1 to 1. Okay, so basically you can figure out from this what is the delta. The delta is the size of the quantization interval, right? And once you have delta and so on, you can easily just use the formula here, right? So we see that, but in fact, I actually do it for you here. The signal to noise ratio at the output of the quantizer is just Q squared, approximated by Q squared, where Q is the number of levels. So in fact, you can just use that here. Okay. So that's question 3. And question 4 says, if you're given this signal here, find the quantization interval and the minimum sampling frequency for PCM when the number of quantization levels is 64. So again, you have to think through it, go back to here and understand, you know, the setup. So this is the setup, and this is also part of setup. We're defining the quantization error. And then this is the analysis. With that setup, the analysis of that is going to be relevant here. And this analysis is very nice because it gives us a nice rule of thumb. It says if you add 1 bit to the quantizer, you get a 6 dB gain. So this is nice because it allows you to do like back of the envelope calculations of how many bits you need for your quantizer. Okay, so I think so again, 1, 2, and 3, I've pretty much walked you through. 4, I haven't. But I think if you understand 1, 2, and 3, you should be able to do 4. And that's all you have to submit. Okay, but you know, there's a whole bunch of other questions that you should work through. And if you have questions, please ask. Okay, so that's the idea behind, if you go back here, sampling we know, it's just Nyquist. Quantization, now we know, we understand a little bit about quantization. Then we're going to generate a waveform. And the next part of this, these notes here are about the waveform here, right? So we're going to generate so-called waveforms here. So these are the PCM waveforms that we're going to actually use to transmit and possibly possibly modulate. Okay, you can generate, you know, like, well, you're going to generate a sequence of 1s and 0s, right? So if you do unipolar signaling, it's either 0 or 1, or bipolar is either -1 or +1, or sometimes people call this polar, and bipolar is reserved for something like this, where you have 3 levels, 1, 0, and a -1. Okay, but I think you can. Let me see. You call it line coding, and you can look at the Wikipedia for line code, and this will kind of give you a, maybe I don't think that's there in my notes. I often give you stuff in my notes, but I think I did here. There it is. Okay, you can look at this link here. Okay. And yeah, so this right here, this generating these waveforms from the bits is this process here. If I go back here, is this encoder. This encoder is what is going to do. Yeah, I think if you watch the video, the reason I called it 1, 2, 3, 4, 5 is in the video I talk about it. Ken Lee or Jia Kang, do you remember from the video? I explicitly talk about these things, right?
Yes.
Yeah. So like anytime, yeah.
Yeah, you did explain every block of the.
Yeah. So anytime you see any of these blue annotations, it's explained in the video. Okay. All right. So roughly that's quantization. So can I check? Are there any questions on either the notes or on the homework that I can help with? Right. If you don't have any questions now, maybe you haven't had a chance to go through it. It's fine. If you do come up with questions, just post it here. You notice that some of your classmates have already been posting some questions, right? So, right. So please go ahead and take advantage of the fact that either I or Kaysun, so I sometimes answer it while I was away. I think Kaysun was answering some of the questions. Yeah. Yeah, I think this is from Kaysun. Okay. So are there any other questions? So the last thing I will do is let me bring up the activity. So remember I told you in files, in Canvas files, activities. There's this file here. Okay, that's the last thing that I want to do. So let me open it. Okay, and let me share my screen. Let me add this, Microsoft Word. Okay, can you guys see the Microsoft Word file? Right, there were 10 questions here. So we'll go through these 10 questions, okay? Can everybody see this or not? Is the Word
Yes, yes.
file, is it visible?
Yep.
Okay, great. Okay, so let me look at the time right now. Okay, 7:23. What do you guys want to do? Do you want to go through these 10 questions and end? Or would you guys like to take a break? Can I get an indication from you guys? Whoever speaks up, your vote gets counted. So do you guys want to take a break? Maybe like a I don't know, 5 or 10-minute break and then finish this, or just hammer through this and get done early? Quiet, all quiet.
Because I wouldn't want to be the guilty one.
Okay, what about you, Chihui? Are you trying to say something?
Let's break.
Okay,
Okay. Yeah.
let's take a break, but can we keep the break short?
Sorry.
Like, would that be okay if we take a short break?
Oh yeah. I mean, take a short break.
Yeah.
Before we start.
Okay. What? When? So Chihui, like I said, since you spoke up, your vote counts. So how long a break you want to take?
5 to 10 minutes. Okay.
Let's do that. Let's take a 10-minute break. So we'll come back at 7:35. Okay. So right now it's 7:25. We'll come back at 7:35, and I'm gonna go and try to fix my circuit breaker. Find out what's
Thanks.
wrong. Okay. All right, guys. So I'll come back in 10 minutes. Okay. Thanks. If you guys do come back early and so on, please start working on these problems. Okay. I'll tell you a little trick. If you start working on the problem and you get stuck, when I show you the answer, it'll be a lot more meaningful. Right? If you just sit back and listen to my answer, you won't really learn. You'll just learn what the answer is. You won't learn how to solve the problem. So my suggestion is, at least, to be honest, the first 4 are quite easy. So go ahead and start working. Actually, the first 5 are quite easy. So please start working on them. Okay. So again, I'll see you at 7:35 p.m. Okay. Thanks, everyone. Have a good break. Okay. All right, everyone. Apologies, we went ahead without recording, so I'm going to just review. So when we came back from the break, we started looking at these problems here, and we were looking at the problems. If you go to Canvas, Files, Activities, you will see a file here called TEE3131 sample problems. That's the problems that we're looking at, and we started looking at the first few. So problem 1 was about what is sink convolved with sink, and the solution is here. Essentially, you're going to look at convolution in time as multiplication in frequency. So we take the Fourier transform of sink, which is rect, which is shown here. And so this is sink convolved with sink. In frequency, it's the two Fourier transforms of sink multiplied together. So that's rect of f times rect of f. But if rect of f looks like this, then rect of f times rect of f is just rect of f, and you take the inverse transform to get sink of t. So you get that sink squared, sink convolved with sink is just sink of t. Okay. The second question, we take the same, we take a signal, m of t equals sink of 300t, and you want to ask the question, what is the bandwidth of that signal? And for that, we just need to realize that when you scale something up in time, like sink of 300t, the Fourier transform is just 1 over 300 times rect of f over 300. And when you want to draw this out, it looks something like what's shown here, right? Which clearly has a bandwidth of 150 hertz. And then as Tintin was telling us, for question 4, if you have a signal with a bandwidth of 150 hertz, the minimum sampling rate is twice that. So it's 300 hertz. Okay, and that got us to question 5. And in question 5, we are saying, let's say the message signal is 0.5 cosine of 2 pi FMT, where FM is 10 kilohertz. Okay, and the carrier is 200 cosine 2 pi FCT, where FC is 1 megahertz. What is the spectrum of the double sideband suppressed carrier AM signal? Okay, does anyone know what it looks like? We did this a lot when we talked about AM. Jiekang, do you remember?
I think I forgot already.
So again, we're gonna do the same thing, right? So my modulated signal U of t, what does it look like? Not look like, but what is it? It's just M of t multiplied by C of t, right?
Yeah.
Right. That's amplitude modulation, right? And so again, multiplication in frequency is what? I said multiplication in time is what in frequency?
Convolution.
Yeah, it's going to be M of f convolved with C of f, right? So what does if this is M of t, what does M of f look like? Jiekang, what does M of f look like? If this is M of t here. Jiekang, do you
Is
know?
it a pulse?
Right, the impulses where? Basically at
At
plus or minus
FM, yeah,
10,
so
right?
at 10 kilohertz.
Yeah, so I have a pulse here, a pulse here at, so this would be 10, I just call it 10K, okay? I'm trying to write with my trackpad. It's a pain in the neck, okay? And then what, and then what is this height gonna be here?
0.5?
No,
Wait, no.
close,
0.5 over 2.
right? So it'd be
Yeah, I forgot.
1/4, yeah, exactly. Okay, so this is M of f, okay? And what does C of f look like? Who wants to tell me? Someone else? Tintin, what does C of F look like? The Fourier transform of the carrier.
There will be two impulses at plus and minus 1 megahertz.
Yeah, exactly. So we get 1 megahertz and minus 1 megahertz. Correct. And what's the height going to be?
100.
Yeah, it's going to be half because this 200 has to be split between the two. Correct. Exactly. So now we know M of F and C of F, we can now convolve them. So does anyone know what the convolution of these two is? It's quite simple, right? And we did this a lot already, right? When we talk about double sideband suppressed carrier. Oops. Okay, so we're going to get something centered around 1 megahertz, right? What are we going to get? Does anyone remember? So this is going to be 1 megahertz and minus 1 megahertz. And what do we get around that? Around that, we get the spectrum of M of F, right? So there's going to be M of F here. Its height is going to be basically 100 times 1/4. Height is going to be 25. And where is this? What point is this?
1 megahertz plus 10 kilohertz.
Yeah. So it's 1 point 10 kilohertz. Hang on. 10 1. Wait, hang on. 1 2 3, right? 1 2.01. So 1.01 megahertz, right? And this point is going to be at 0. So it's 1 megahertz minus 10 kilohertz. But if you convert everything to megahertz, it's 0.99 megahertz. Okay, this is what the spectrum of the double sideband suppressed carrier looks like. This is U of F. So is that clear? Like for example, who was I asking before? Tia Kang, yeah.
Yes, yes, this is clear. Yes.
Do you recall this now?
Yeah, I recall.
And then remember, if M of T is something else, right? It doesn't have to be the impulses. If M of T was a triangle, you would just get the triangle replicated here, right? At 1 megahertz, right? Yeah. So if M of F happened to look like the triangle function. Okay. But the answer to this question is there. Okay, so is that clear to everyone? Is there someone is not clear? Can I check Yang Bo 1? Is this clear? Are you guys following along? Tintin, is it clear?
Yes, bro.
Okay. Bo 1, are you around? Is this clear? He might have stepped away. Okay. Okay, then this one. Whoa, something happened. Okay. This one is quite straightforward. Why do we, for conventional AM, why do we need this condition? For this one, you can just go straight to, you have to recall the AM notes. Let me hang on. Let me bring this up. Wait, what's going on here? Give me a second. Oh no, I uploaded something here. I didn't want to. I uploaded the wrong thing. I uploaded it here by mistake. What I want to do is I wanted to open it. to come here. What do I open? Conventional. There we go. Okay, there we go. Yeah, and with conventional AM, you guys remember this picture? This picture here? This picture tells you why 1 plus MFT has to be greater than 0, because when it's not greater than 0, when it crosses 0, for example, then the envelope will cross itself, right? Do you guys remember this? Yeah. And when the envelope crosses itself, it gets distorted. You can't recover the envelope. The actual envelope is distorted. The actual envelope, yeah, it doesn't look like this. It doesn't look like this anymore, or this. Envelope looks like that. Okay, so that's the reason. So you basically, the answer to the question here is we need the condition so that the envelope of the message, of the modulated signal is equal to the message signal and not distorted. Because if 1 plus M is less than 0, as we saw here, it can get distorted. Okay, so that's the answer to question 6 here. Let's look at this one. So question 7 says, consider the spectrum of upper sideband AM. Okay, so this is no longer double sideband, but it's upper sideband. And this is the spectrum here. And the question is, by inspection, so you can do this by inspection, actually, meaning by just looking at it. There's no computation to do, but you have to understand. So this is more of an understanding question. What are the carrier frequency and the message signal? So can anyone look at this and tell me what's the carrier frequency? Assuming this is upper sideband AM. So who can help me with that?
Carrier frequency is 5 kilohertz.
Yeah, exactly. So the carrier, Tintin is exactly right, is right there. Okay, so we can say that the carrier FC is 5 kilohertz. Okay, and then if remembering that this is the upper sideband, meaning we threw away the lower sideband, what's the message signal look like? Does anybody know? Tintin, can you look at this look at this and tell me what does the message signal look like? What's the Fourier transform of the message signal? This is the Fourier transform of the modulated signal. So what's the Fourier transform of the message signal? So remember, we threw away the lower sideband. What happens if you add the lower sideband back?
The triangle.
Yeah. So the message signal looks like you have, this is the upper sideband here, but there's going to be a lower sideband. So this is what the message signal looks like. At least the Fourier transform of the message signal. By the way, these are, in case you didn't get it, these are supposed to be straight lines. Okay. Maybe I didn't draw such a straight line, but it's supposed to be a straight line. Okay. Maybe I'll fix the other one too, just so it doesn't look so bad. Okay. So if this is M of F, what's M of T? Do you know, Tintin? If this is M of F is a triangle, what's M of T? By the way, we didn't fix this. What is this quantity here? What at what? How far does this go out?
0.1 kilohertz.
Yeah, which is what? 0.1 kilohertz. What is that? 100 hertz?
100.
Yeah, it's 100 hertz, right? Okay. And then what's this height? So the AC by 2 is because the carrier gets split, right? So what's left is 1 over 100. So this is 1 over 100. Okay. Okay, it's 1 over 100. All right. So what is MFT? From this, can anyone tell me? First of all, what's the inverse transform of a rect of a triangle?
Sin square.
Yeah, it's a sin squared. So this thing, you know, is going to look like something like a sin squared, right? We just don't know maybe some of the scaling stuff. It's going to be sin squared of something. Now, Kenley, do you remember before we had this?
Yep.
We had this relationship that when you multiply the inside by something, this is what happens, right?
Yeah.
So we kind of have this here, right? So what do you think? I have a 1 over 100 and 100 here. So this looks like sin squared goes from -1 to 1. This goes from -100 to 100. So what do you think the inside here is?
200.
Huh?
F 200. No.
First of all, it's not F. This is an F. I'm going to T. So this is going to be T over. No. No, it's going to be.
T over 100.
No, it's not. It's going to be 100 T. Right?
Yeah. Correct.
Because if it's 100 T, then based on what we looked at before,
Yeah.
right? If I have
Mm.
BT, then there's the 1 over B
Mm.
and an F over B here. And we see that because since the triangle goes from -1 to 1.
Mm.
This is
Mm.
like triangle of F over 100, right?
Yeah.
Yeah, so this is the answer for MFT. So MFT is sin squared of 100T. Okay, so again, this is really just inspection and realizing some Fourier transform results. So is this clear to everyone? Jie Kang, is this clear?
Yep.
Tintin?
Yes, bro.
Okay, good. Let us. Oops. Let's go to here. So now I am looking at phase modulation. Okay. And in phase modulation, I want to find the bandwidth. So I have, again, sync of 300T is my message signal. And I'm going to do phase modulation with that, with the phase deviation constant of Kp equals 5. The question is, what is the bandwidth? So of course, we're going to use Carson's rule, right? So you got to remember that. Carson's rule for AM and FM, Carson's rule is the only tool we have. And Carson's rule is 2 times beta plus 1 times W, which is the message bandwidth. So all we got to do is figure out these things. So with sync of 300T, what was the message bandwidth? We did this already, right? What's the message bandwidth? We did this already, but you can just recompute it, right? We did it up here, right? In question 2. So what's the message bandwidth?
150.
Yeah, 150 hertz. What's beta? Beta was the modulation index. And if you went to our notes for FM, and we wanted to compute from Carson's rule, you go to the Carson's rule section here, right here, right? So beta is just this, right? It's just Kp times max of M of t. So it's Kp times max of M of t. Okay. And what's max of M of t? For sink of 300T, what's the maximum value? Well, the maximum value is going to happen at 0. And what's sink of 0? Right? So for that, you have to remember what the sink function looks like. Right? The sink function looks like this, right? Sink of 0 is the maximum value. So what's the maximum value of sink of 300T? What's this max here? So it's shown here. I'm plotting sink here. This, like this red here is the sink function.
1.
It's going to take a maximum value of 0. So even though it's sink of 300T, its maximum value is still going to be at 0, which is the same as what's shown here. So it's 1, right? So this is 1, and Kp is 5. So it's 5 times 1. So beta is 5. So now we can easily compute Carson's rule. So Tia Kang, what's the bandwidth according to Carson's rule? Two times 5 plus 1 times 150. So what is that?
$1,800.
Yes, 1800 hertz, right? Okay. So again, 8, not that complicated. You just need to make sure you understand some basics here, right? And so remember that for AM and for FM and PM, for the angle modulation, meaning phase modulation and frequency modulation, really the only two we have is Carson's rule. Okay. All right, great. So Kenley, is that clear?
Yes.
Okay. Let's look at problem 9. So this is now moving on to quantization. So PCM and quantization. And let's see. Maybe you can help me with this, Tintin.
Nice.
Yeah. You want to try problem 9?
Oh, okay.
Try it. Don't be scared. Yeah. So we have a 6-bit quantizer.
Mhm.
We have a signal with a dynamic range of 0 to 256 volts. And the question is, what is the minimum expected output bit rate after sampling and quantization if the input signal has bandwidth of 5 kilohertz? So how are we going to do?
So is 5 kilohertz times 2 times 6.
Right. So the bandwidth is 5 kilohertz, which means what?
5
So if-
5,000.
Yeah. So that means sampling rate is
5,000 samples.
no. So if you have a bandwidth of 5 kilohertz, what's the minimum sampling rate required?
10 kilohertz.
So Tintin, I noticed that when I ask you the question, you know how to answer it. What you have to do now is learn to ask the question.
Okay, bro.
No, yeah. So let's go back. So remember, we're trying to figure out. So remember, this is the figure that we drew before, if you remember. We have two things here, right? One is the analog signal comes in, then we're going to sample it, and then we're going to quantize it, right? So if a 5 kilohertz signal comes in here, and this is the sampler, you have to ask the question. The first question you have to ask is, okay, because I have to sample in time and quantize in value. So whenever you have this signal that you're going to process, you got to sample. You got to ask, what's the sampling rate, right? Do you get it, Tintin?
Yes, bro.
So so the reason I wrote the bandwidth is 5 kilohertz implies what? What does it mean if I have a 5 kilohertz signal?
That means there will be 5,000 samples per second.
So is that how you would sample it?
No, there will be 10,000 samples per second for
Why?
sampling.
Why? Yeah. Can I ask why you say that?
Because that's the minimum sampling rate.
And why is that? Who, like, what result are you going to quote to justify that? Like, how are you going to justify that? Yeah, you're correct. But what's the theoretical result that justifies that?
Nyquist theorem.
Right? It's the Nyquist sampling theorem. So by the Nyquist sampling theorem, what do you have? That the sampling rate should be what?
Should be at least twice the
Right. Yeah. So I know when I say the answer, you've been programmed to give me the right answer. But what you need to do now is you have to ask the questions and construct the answer by yourself. Do you get it now?
Okay, bro.
Right? No, I mean, this applies not just you to all of you. So thank you for interacting with me. Okay. So the first step in this is, yeah, I mean, if you're just given a question, you don't look for a model answer. You have to learn to think. And, you know, after experience, you realize that, well, if I'm talking about sampling and quantization, the first thing I got to figure out is, okay, what's my minimum sampling rate? So minimum sampling rate here is 10 kilohertz. So now what? Now what's the next information you're given? So this means I have 10,000 samples per second, right?
Yeah.
Sampling rate of 10 kilohertz means 10,000 samples per second. Great. Now what? What's the next piece of information we are that we are given?
The number of
Yeah, exactly. So now we know that we have a 6-bit quantizer. And what does that tell me? Well, means I have 6 bits per sample, right?
Yeah.
So now can you figure it out? What's the bit rate at the output of the quantizer? What is it?
6 times 10,000.
Yeah, I mean, do you can you see that? I have 10,000 samples per second. Each sample uses 6 bits, right?
Yes.
So this is like times 6 bits per sample. That's going to equal what? What's the data rate in bits per second?
60,000.
Yeah, so 60. So maybe we kilobits per second. That's it. So do you see that this is the same computation that we did before?
Yes, bro.
You remember we did? Yeah, so it's the same computation. Okay, good. Thank you very much, Tintin, for working with me. Okay, let's look at the last problem here. So who's going to help me with this? Can I get a volunteer? Can I get a volunteer? Don't leave me hanging, people. Okay, how about I'm gonna build a super volunteer. Ken Lee and Tia Kang, you guys work together.
I'm about to tell you my brain burned out.
Wow.
What?
I'm about to tell you that my brain has burned out.
Okay, that's why I'm gonna put you guys together. You each have half a brain. Now you have a full brain. No, I'm
Thank
just
God.
kidding you. No. You don't have half a brain. I just meant why you guys work together so you can learn from each other. Okay, so come. I'm the one with half a brain right now because I have no power in my house.
Okay, sure.
Seriously, after this I've got to go and figure out how to fix my fuse box.
Yeah.
Okay, so let's do this. So guys, so we have this is the same setup. We have a 6-bit quantizer, and we have the dynamic range of the quantizer of the input signal is 256. It can go from 0 to 256. Does everybody understand that's what this means? The input
Yeah.
signal that I'm quantizing can range from 0 to 256. Okay, and then the question is, what is the maximum quantization error when, it's very important, when uniform quantization is used, okay, and X falls in the range from 0 to 1, okay? I mean, if the particular X is in 0 to 1, what's going to be the maximum quantization error? So and then we're going to assume uniform quantization so that the quantization levels are chosen as the midpoints of the quantization bins. Okay, so remember in quantization we are binning, right? So imagine you have this.
Correct.
So what you have is you have this range from 0 to 256, right? Your signal can be in this range. We're going to use 6 bits for the quantizer. So how many levels are there? Right? Because we're going to take this range and chop it up, right? That's what
64.
quantization is. Chop it up into bins. So if I have 6 bits, how many bins do I have?
64.
64
Right.
bins.
So I have 2 to the 6, which is 64. They could be called bins, or sometimes we'll be calling it levels, right? 64 levels, right? But sometimes I like to say bins as well. 64 bins. Okay, so that's sort of step 1. Okay, I have 64 bins. Now, if you have 64 bins or 64 levels, and the range is 0 to 256, how big is yeah, exactly, Candy, how big is a level? It's going to be 4 volts, right?
Yep.
Because, well, 256 divided by 64. Okay, so each, and this is what we call in the notes, I call this delta. This is the bin size. Okay, so the bin size is delta. This bin size is essentially 256 over 64. Okay, and that's equal to, in this case, 4 volts. Okay, great. So this is good. So now we're getting somewhere. Now imagine we're at the lowest bin. Okay, here, from 0 to 4, right?
Yep.
Hang on. I want to draw this a little bit better. That's horrible. Okay, 0 to 4. Jikang, are you with us?
Yep, I am.
Right, and assume now we're using what type of quantization?
Midpoint quantizer.
Right? So a midpoint quantizer. That means if you look here, oh, that's really thick. Let's try that one. Yeah, we're gonna use. Oh, I don't like that either. Hang on. Let me try to find one that I like. Okay, here we go. We're gonna have a midpoint quantizer. That means in this bin, the value of the level in this bin is gonna be here. So this is 0. This is gonna be 2, right?
Yep.
Okay. Now it says, okay, I'm gonna assume that a current input is between 0 and 1. So this is 0 to 2. So let me change color here. Suppose that I have an input that's here, right? This is, oh, this is horrible. Okay, I'm in the 0 to 1. So this is 1 here. So I'm in 0 to 1. Oh, that's, can't draw this properly. Okay, now the input falls in this range. The question is, what's the maximum error?
1.
Okay, so that means, so remember, for a midpoint quantizer, anything in this bin is represented by what? So any value from 0 to 4, what will it get mapped to?
2.
2, right? So anything in this bin will get mapped to 2. What's the maximum error you can have? Why is it 1, Kenley?
Because its actual is 1, then it will pick up the quantized value of 2.
Right, but we
That's
said
minus 1,
maximum
sorry.
error. What's
should
the
be minus
maximum error?
Okay.
For example, if I told you that the value is between 0 and 1, right? Suppose the value is close to 0. It's down here. Then what's the error?
0, minus 2.
Almost 2.
Yeah, it's almost 2. So what's the maximum error, Kenley?
2.
2, right? Not 1. You're counting from here.
Yeah.
But you actually have to count from here because I told you that X, like when X
understand,
is in the
understand.
range 0 to 1, what's the error?
Yeah, understand.
Yeah. So we see that. So again, the story is that in a midpoint quantizer, everything gets mapped to the midpoint, to 2. And actually, I didn't even have to tell you that X is in the range 0 to 1. I could have just asked you for X in this range from 0 to 4, what's the max error? It's still 2, right?
Yeah.
No matter where you are in this interval, the farthest you're away from 2 is 2. Right? You could be here, near here, or down here. The max error is 2. Right? So yeah, so the maximum error is this.
Yep.
Okay, so the max error is 2. Okay.
Okay.
And that answers this question. Okay.
Right.
Okay, is that clear, Kenley and Cheka?
Yes.
Yes.
Yeah. How about the rest of you? Tintin?
Yes, Prof.
Yeah. Okay. Good. So that's it. So I hope that these questions are useful. I can actually upload this to the. I mean, it's already there in the video, but I can upload these marked up notes to the activity sheet as well. Okay, and I will do that. Okay. So are there any questions on this or anything else? So remember that I'm going to be putting up. Let me see. Can I? Hang on a sec. Oh, did I? No, hang on. Yeah. So this is our schedule, right? So what so there's going to be like a minor change to this, and I'll update it, but I can share the minor change now. Roughly, what we're going to do is we're not going to have the DM here or here. Actually, the DM can be here because I'm going to upload it today, but we're not going to do DM here. We did problem solving today. This will become DM. Okay, digital modulation, and then we're going to basically shift everything down. Okay, so this one will be source coding. This one will be source coding and the beginning of channel coding. And then this one will be channel coding. Okay. So we just shift everything down by one, roughly. Don't forget, we have our quiz. The quiz is not next week, but the quiz is in 2 weeks from today. But I'm announcing here, so this applies to all of you watching on webcast who didn't come. There's going to be a graded activity next week. We're still going to be remote. Okay, it'll still be remote. We're not going to do face-to-face, but there's going to be a graded activity in class. All right. But the following week, we're going to be face-to-face for the quiz. And the quiz will be a pen and paper quiz. The graded activity will be remote. Okay, so is everybody clear on that? So for next week, actually, attendance is required. And this applies to everyone. The folks who came here and the folks on watching this webcast. So if you have friends who didn't come today, please let them know. I'll also be sending out an email to remind people, but we're going to start talking about digital modulation, and there's going to be a graded activity. Okay. And also next week, your next Friday, your lab is due. Lab 1 is due. So you can ask me questions about that. And if you need to set up a time with the TA, we can do that. Okay, so any questions, any thoughts? Anybody have anything to share?
Of the lab 1, on the question 2, don't really understand.
Lab
Can you-
1.
Yes.
Let me find it. I actually don't have it. Let me. I'm gonna have to go to Canvas to get it.
Do you want me to share or?
Yeah. Why don't you share? Kenley, if I can't answer this, what we'll do is you can maybe just post it to Piazza and Liwei will answer it.
I just want to get a better understanding. You able to see now?
Yeah, sure. Yeah. Show me now.
Okay, so I just want to get a better understanding of what's written here. So
Yeah.
I don't really know how to read this. Yeah.
Like all this is saying is that that the different signals, okay, are use different parts of the band.
Yes. But how do we, if you're talking about getting the original left and right, there is L to the T and R to the T, but there's a few left and right. So I get very confused on this.
No, so so you can look at the mono as well as the stereo, right? So the mono is here and the stereo is going to be these two, right?
Okay.
So what Liwei is showing you here is he's showing you what the FM spectrum looks like. That when the mono audio is sent, it's sent in this range here. Stereo is sent in this range.
Okay.
Yeah, I think that's all that's being trying to get across here. And notice that this is yeah. So that's all. So when you actually look at the spectrum, right, you're going to be able to look at the spectrum in GNU Radio. You should be able to see this.
So does it mean that we're going to get a low pass filter and map the mono audio and the
No. When you look at the spectrum of the signal, you
Okay.
should be able to identify this.
spectrum of the signal? Okay.
Yeah,
Maybe
because in lab 1, you're building an FM radio, right?
Yep.
So you have actually the FM signal, right? What they're telling you here is that the actual FM signal consists of all of these components.
Okay.
And so when you take the FM signal and you decode it and then you take its spectrum, right? This is what roughly you should see something. Now it's not going to be as clean, right? It's going to be a bit noisy, but you should be able to identify these different portions.
Okay, give it a try. Yeah,
Yeah.
thanks.
Yeah, and then what you want to ask is, so this is asking you, how am I going to recover? You know, given this spectrum, how are you going to recover
Back to
your
the origin.
actual the information signal? But it's okay. I think if you have questions, you can post it to Piazza,
Sure.
and I'll instruct Leeway to help you guys
Okay.
as much as is necessary. Okay.
Okay.
Yeah.
Thanks.
Okay, thanks. Yeah, thanks for the question, Candy. So if you guys have not started on lab 1, please get started on lab 1. So again, to summarize, maybe I just bring my things back up, right? I go back to Piazza here. The things on your plate, you have lab 1 due today, lab 1 due next week. You have problem set 3 due this week. Okay. If you haven't finished the task for PCM, then please do that. And then be on the lookout for the task for digital modulation. Okay. I suggest you spend some time this week and this weekend working on digital modulation so that you don't get left behind. Okay, great. So I think that's all I want to say. Are there any other questions? No? Okay, so I think we can end the session today. Thank you, everyone.
Thank you, Prof.
Well, thanks.
Thank you, Prof.